Welcome to my presentation held at the AMI Wood Plastic Composite Conference in March 2016 in Vienna. My name is Dr. Daniel Friedrich and I'm conducting research under the research label Compolytics, which is Composite, Polymer and Policy Analytics Independent Research. I would like to report on test results, and it is norms and performance tests for wall cladding made of WPC, where I want to explain how WPC facades are designed by engineers in order to prove their fitness of use in the building scope. I would like to start by providing insights about who is responsible for the structural safety of such facades in practice, which are decisive product properties to be tested and used in such design procedures. Then providing the results from a study conducted by Compolytics, how to gain such design values, and then closing my presentation with a summary about the lessons learned. So this marking obviously indicates that there is a compliance of the product with a norm, and this then ensures that stability as demanded by codes and by law is given. So which attribute stands for such a cladding stability? And here we find further norms like the DIN norm 18516, cladding for external walls ventilated at rear. And here principles are for the calculation of material stresses, deformations and the fixation resistances are explained. And there are also international, so European norms like the European Technical Approval Guideline, the ETEC 034, released in 2011 for ventilated cladding kits comprising cladding components and associated fixings. And here it is explained that the resistance can be received by resistance tests like wind tests in a suction chamber or foil back test. These tests illustrate wind suction on a test facade, from which the facade's resistance against such wind loads can be derived. And there's also the EN 15534, which is explicitly released for WPC compounds, where in part 1 also test methods for the characterization of such compounds and products are explained. So this is not for a facade section, but it is for the material respectively, where characteristic compound properties like the modulus of rupture or modulus of elasticity and also the fixation resistances are explained by respective tests. Such wind suction tests can be a wind suction chamber as shown in this graphic here, or a pull-out test of the single fasteners, which is shown in this illustration here. So by applying a cyclic wing suction on a test facade, which is shown here, we can measure the wind load resistance in kilonewtons per square meter, but we also receive particular resistance values for the single fixations within such a facade section by these pull-out tests. So why wind suction and not only the pressure is tested? Well, if we have a building, there is a wind blowing on the building, and on the one side there is of course a positive wind pressure pulling or pushing the facade to the subconstruction, and this is not so critical because the loads can then easily be transferred from the facade surface to the subconstruction. The more crucial case is on the opposite side of the building, where we have wind suction, and here this is a much higher stressed impact on the facade, also for the single fixation points. So here we need explicit information. What is the load resistance for wind suction of such a facade cladding kit, like WPC facades, inclusive their respective fixations? So how we can then perform a strength proof is explained by the Eurocode EN 1990, the basis for structural design, and the resistance is proven if a facade's resistance against pulling wind load is slightly higher than the expected impact from wind on a building, and both is in the design state indicated by the index D. So we need information about the resistance values, which were explained in the previous slide by such wind suction chambers or single pull-out tests for the fixations, and this must then be compared with the expected wind loads, and these we receive from norms where for the regions such expected wind loads are properly explained, and these values can be taken from the norms, but we need these resistance values from the facade cladding suppliers, and they hopefully have conducted these testings, but since this is in the design state, they must transfer the test results from such wind suction chamber tests, which are still in the characteristic state marked by the index K, to the design state D, and this is done by multiplying this characteristic wind resistance value with a conversion factor taking into account the material and product aging over its lifetime, and by dividing this characteristic value by a safety factor, which for cladding and facade usually ranges between 1.5 and 2.5. So now it's more about how to get to this conversion factor nu. So to know more about these characteristic wind load resistance values for cladding, we have been conducting such wind suction tests using the foil back method, where we erected facade section with WPC cladding profile as shown here, with a polyethylene matrix and 60% fiber share, and then we were building a 2-field spanning facade section where these foil backs were underneath, and then they were filled with pressured air, and then we measured the pressure in kilonewtons per square meter until this wind suction failed, and we were observing what is the failure mode, either a bending rupture of the facade panel itself or a failure of the fixation points. The results are explained and already published in the Journal of Building Engineering, easily to be found by this reference here. So what we measured was failures which only occurred by an edge cracking around the fixations, so this is obviously the most important failure mode. And we measured values depending on the field span, ranging from 400 to 700 millimeter span, and the rupture values, so the simulated wind suctions, were 5.8 kilonewtons per square meters, going down to 3.8 for the widest span. And this is also illustrated by these curves here. So the conclusion is that the prediction of a WPC facade failure is the resistance of the value of the fasteners and not a breaking of the facade panel themselves. And the characteristic values, they range from 5.8 down to 3.8 kilonewtons per square meters, depending on the sub construction. Now we can use these values as characteristic values, which now must be transferred to the design state, and by a literature research covering a wide range of single material testings in the field of WPC, we found that the aging of material WPC by fungal decay is something like 14% from the virgin state. Aging through natural weathering, which is UV radiation, is about 3%, and aging by frost thaw cycling is round about 15%. And then we get a global aging coefficient by multiplying these three values with each other, and then we get in total a conversion factor of 0.49. So round about 50% of the virgin material resistance value is applicable for the design state. So multiplying now the characteristic values with this conversion factor here and dividing the result by a chosen safety factor, which is 2.0, we get design values with which we can then make the proof for such WPC facades. The results are shown here. So we've now taken the test results from wind suction test 5.8 to 3.8, multiplying them with the conversion and dividing them by the safety factors, and then we end up with design resistance values ranging from 1.42 down to 0.93 kilonewtons per square meter. So with this information we were finally able to do a strength proof, and taking the position of a facade engineer, for example, and then we were assuming a building located in central Germany, let's say in Frankfurt, for example, and from the national wind code we received a characteristic wind suction value to be expected here in this Frankfurt region for a lifetime of 50 years, and this characteristic wind suction is 0.91 kilonewton per square meter, which now must also be transferred to design state by multiplying it with a factor of 1.5, also well described by this norm, and then we end up with a design wind suction value of 1.37 kilonewtons per square meter. And now the resistance value must be slightly more than this, and we were able to take from the previous result a value of 1.42 kilonewtons per square meter, which fits to a 400 millimeter span distance of the subconstruction. So this is then the result of our strength proof. This WPC facade can be used for this building project if the subconstruction shows a span of 400 millimeters. So let's sum up. What we learned in this presentation is that house owners, contractors, planners and site managers, they are deciders and must ensure compliance of the selected WPC cladding product with respective norms. These norms demand stability from such a WPC facade, which is given by stability checks from strength calculations, which must be undertaken from these responsible persons. So this is a overview about the respective norms and also the codes which are applicable for such strength proof of WPC cladding kits. Now I would like to come to the end of my presentation. Thank you very much for your attention, and if you are interested in further information, please visit the Compolytics website shown here. Thank you very much.